Hello. Okay. So, what today we're going to do is we're going to essentially look into this book called Introduction to Mathematical Statistics by Hogg, McCain, and Craig. It's a pretty standard book. Today, what we're going to understand is what we're going to study uh, within this book, right? So, first thing we'll say is the probability and distributions. Okay, it will talk about set theory, the set function, essentially the probability function, condition probability, and independence. And it will define random variables. Then it will talk about discrete and continuous random variables. Then we'll see what the expectation of a random variable means, some special expectations with some different forms, and some important inequalities to look into. Then I believe there will be some exercises after that which we can also look into. Then there will be multivariate distributions, distributions of two random variables. So essentially, we defined a random variable. What is a random variable earlier? Now what we'll understand is how multiple random variable can be jointly represented. All right. Then we'll look into the transformation of those particular random bivariate random variables, like the joint distributions transformations. So you will see here as well in discrete and random variables and continuous random variables as well. There are some transformations mentioned, which essentially transforms the space. The it can be a real space or some different kind of space or from that set to another space, and how we will define that we have to look into depending upon the random variables. Similarly, we can do that for joint like bivariate random variables as well. Then we'll look into the conditional distributions, probably marginal distributions as well, and their expectations. The correlation coefficient. Correlation is essentially the degree of association between two random variables. And then independent random variables. Okay, what is independent random variable? What does it mean to be an independent random variable given another random variable? Multivariate covariance variance matrix, which is very useful when we move into actual multivariate analysis, and transformation of several random variables, linear combination of random variables. Essentially, we can combine some of the random variables together. Right, all right. Then we'll look into some of the most common distributions: binomial, Poisson, chi-square, beta, gamma, the normal distribution, multivariate normal distribution, I think multivariate multinomial distribution is another one. I don't see that here. It's all right. Then T and F distribution, students' theorem. All right. Students' T will get to see. Now, the interesting part that essentially is the backbone of statistics will come into play. Essentially, we'll look into sampling, how sampling gets done, and why sampling is required, and how can we ensure a proper representation of the population, which is underlying. Histogram estimates of PMS, and okay, histogram I think we'll get to see when we reach there. Confidence intervals. Confidence intervals essentially means we define a range. We do not give a exact estimate. We give a range of a particular estimate, and we say that we are very confident or X amount of confident within that the actual population mean lies in between that interval. We'll get to see that later, but I'm just giving a brief understanding. So when you have completed, like when we have completed through this whole thing, we can come back and look into this video and we understand what we are meaning when we are saying these things. Um, Confidence interval for parameters of discrete distribution essentially, yeah, that's what I just told you. Our statistics, quantiles, confidence interval for quantiles, introduction to hypothesis testing. Lot of hypothesis testing can be done. There are several tests, chi-square test. Okay, there's nothing else here. Okay, no worries. Mon okay, Monte Carlo simulation, accept reject generation algorithm. All right. Bootstrapping, percentage bootstrap confidence intervals. Essentially, it is used when no particular. It can be used for a lot of reasons, but essentially, bootstrapping is very useful for finding confidence intervals and quantiles as well. Um, Bootstrap testing procedures. Yeah, okay. We'll look into that, what that is. Tolerance limit for distributions, convergence and probability. Okay, center limit theorem we'll get to see here. Convergence and distribution. Then we are essentially like how we were estimating this statistics for the like from we're essentially trying to find out an estimate of a particular parameter through this hypothesis testing whenever we're trying to do. But we'll also see they're called statistics, but uh, when we use maximum likelihood method, that gives another way to essentially estimate those parameters. um, those parameters essentially define a particular distribution or has some relation or connection to the distribution at least. Expectation maximization algorithm, um, multi-parameter case testing, maximum likelihood test. All right. Okay, then we are trying to understand what sufficiency means, exponential clause of distribution, properties of sufficient statistic for a parameter, what does it mean to be sufficient enough, optimal tests for hypothesis, most powerful test, uniformly most powerful test, okay, likelihood ratio test, sequential probability ratio test, minimax and classification procedures, inferences about normal models, human ANOVA, non-central chi-square and if distributions, multiple comparisons, analysis of variance. We'll probably touch very briefly over that. It's a whole another section in it. Regression problem, test of independence, distribution of certain quadratic forms. Okay, non-parametric and robust statistic. Um, Non-parametric is a way where you don't assume. So essentially, let's say, okay, I'll just write something down. Let's say that you have gathered height of 10 students. So 151 centimeter, 172 centimeter. Why am I writing the 182, 140. I'll just okay. Okay. Now, what we can do is we either define a distribution on top of it. So let's say we try to see how this distribution essentially looks. So it can be something like 140 is here, 150, 160, 170, 180. So between 140 and 150, we see only 1 point. Right, between 150 and 160, see 1, 2, 3, there's 3 points, right? Pardon my graphing skills. 162, 171, 2, 3, 3 also here we see. Then 170 to 180, I think we see 2. And above 180, I think we see, sorry, I think we only see 1. So this is essentially called a histogram, right? So this is 1, this is 3, this is also 3, this is 2, this is 1. Let me just ensure that there's some certain 3, 3, 6, 8, 10. Yeah. So one can essentially fit some kind of distributions like this, right, of height. So essentially, this way of creating a histogram is called parametric way. Now let's assume there are two classes. So this data set is from class 1, class A, let's say. And similarly, we have another data set from class B, right? Which also looks something alongside like this. Somehow their height is coming starting from 140. Nevertheless, essentially what we are trying to do when we use parametric way, we essentially try to fit a idea of a distribution, that this distribution looks like this, and we try to essentially find a distribution given the sample data or given the data that we have in our hand. So that is a parametric way, and then we in real world scenarios, these things often, like a lot of variables don't often follow this structural behavior. Then what we can do is we can use non-parametric statistics over there, and we essentially find several tests based on what we want to look into. We want to check if class A has a higher average weight than class B, or less than, or uh, equal maybe, or the variance of. A lot of things can be done essentially. Okay, we'll look into them. um, Simple linear model, okay, Kendall star, Spearman row, location model, linear model. Okay, then we finally dive a little bit into the Bayesian statistics. Bayesian statistics is the most how would I say, is the most necessary one. Um, mm, Not necessary one. It's the most advanced one. Sorry for my phrasing. It's the most advanced one, where we essentially look into sequences of events, and essentially that gives a much better understanding or estimation of a particular distribution. You can see prior and posterior distributions, Bayesian point estimation, interval in estimation, testing procedures. Sorry for that. All right. Then give sampler, empirical base, all right. Mathematical comments, some of these things. Yeah. So essentially, that's what we're going to look into.